Hello and good afternoon, everyone. Maybe it's time we should start this session of Asset Colloquium here. We are lucky here to have a very prominent personality. I'm at a loss of word to describe his primary work because he has done a lot of illustrious things throughout his career. He started with he actually has a history with TFR, if I remember correctly. He had a postdoc here also about 35 years back. Dr. Sadev is trained as a particle theorist in a leading group in Cornell University and University of Pennsylvania and International Center for Theoretical Physics in Italy, among others, where he had very prominent people in the field like Professor Salam, Ken Wilson, Stephen Weinberg, and Richard Feynman is some of his people who have interacted with him extensively on the topics. Then he came to India and joined IIT Kanpur, where he spent almost 22 years teaching a host of students in being a theoretical physics and other fields of things. And many of his research students have then further go ahead and won a very international as well as national awards and things, including Bhatnagar awards and other stuff, things, and other prizes. Yes, and as I've already mentioned, that it is very difficult to describe him as in one particular field because he has tried and succeeded in many of the fields, including going and doing something which is unheard of in the academics. And his career, when he actually started that about 15 years back, when he left the academia and went and started his own company to do something revolutionary. I am sure he will tell us all about what he has done in that part of the things, what he has been journey. And without further ado, I request for
Yes. Okay. Okay, you can hear me. All right. So, yeah, I guess that this topic doesn't quite describe what I'm going to be really covering, but I just happen to give it this particular name because an atomic layer deposition system is the latest thing that we built. But I'll have to give you a bit of the background. I mean, as mentioned, I started out as a particle theorist. In fact, Shiraz was one of the students that I trained. So if you're familiar with him, you know that he is a die-hard theorist. Okay. And and then there are a whole bunch more. I mean, Gopa was another, Rajesh Gopa Kumar was.
Also sent a batch from IIT in 95.
Right.
6 of them in one batch.
Right. I mean, that was one of the 95 batch. Yeah, I invested a lot in that particular batch. I mean, I trained a very large number of students in that one. In fact, we're allowed to teach. In IITK, we were supposed to teach only 1.5 courses in a semester. I'd gone up to 4 courses in an attempt to train all these people in all sorts of different areas. But over time, I decided that if we had to really start doing something in India, we had to build up our own experimental base. And that is what started this whole thing, this whole journey off. And so but what we'll come back to that in a moment. While preparing this talk, I started looking up some of these things. And I was looking at this absolutely remarkable journey of semiconductors, all right? Bardi in Britain and Shockley, they made a transistor for the first time. It was around 1947-48. The paper probably came out in 48, but the discovery was made in 1947. So it was the same year as India gained its freedom, all right? And Shockley wrote the Bible for semiconductors called Electrons and Holes in Semiconductors in 1950, all right? Now, since then, in 1958, Jack Kilby made the first integrated circuit. And it wasn't very impressive. It had just 1 transistor and only about 3 resistors on it. If you look at a picture of that, you're not going to be very impressed at all right? But it started off this absolutely remarkable thing. Moore's law. Moore was one of the people who, Jack Kilby was working for Texas Instruments. and more, along with Noyce, and there were another 6 people who had started out with Shockley and who came to be known as the traitorous 8 because they left Shockley because of his very dictatorial management style. And they joined and in fact effectively started Fairchild Semiconductors in California. So it was Texas versus California, the whole thing. And Noyce was the one who made the first IC using silicon. All right. And that happened in 1959. Okay. And Moore enunciated this law, all right, which was where he said that transistors, which were like the basic element that had to go on the IC, would double every 2 years. So we're talking 1960 and we're right now in 2024. Okay. So that's 64 years. All right. Every 2 years would mean you have a power of 32. So it's 2 to the 32 is the number of transistors that should go onto a single IC. Okay. And 2 to the 10 is 1024. So 2 to the 30 is, 1024 is 1,000, all right? 1,000 times 1,000 times 1,000 makes it a billion. And 32 would mean 4 billion, but the actual number is 114 billion transistors have gone onto a single IC. Okay. This is just quite mind-boggling that you're able to now do this. And what happened subsequently, all right, was that, of course, the entire revolution has taken place. It's computers, cell phones, accelerators, everything. It's just sort of penetrated every aspect of our lives, all right? And the semiconductor industry was, but this in part because of COVID, it went up to 0.6 trillion, but it's expected to cross a trillion in maybe next year, all right? So over this particular period, you suddenly, since the time we got independence, all right, this whole industry has gone up to $1 trillion. It's mind-boggling, all right? And we are still there twiddling our thumbs. There's nothing. It's zero. We haven't earned anything from semiconductors. If anything, the government is putting money into semiconductors, but we haven't earned a thing. And in the meantime, these guys seem to have built up and completely transformed the world. Now, I was quite zapped by all this. So, the point is, what do we really need to do in order to get somewhere with this? Okay, so now this is essentially the theme, all right? Now, let me explain this in a slightly different way and start relating it to what we are doing, all right? If you just open out your computer, all right, you'll see a board like this, and all the components on it will be on the scale of centimeters. You go one step further and you look at just one small part, you see all these tracks out here, which are on the scale of millimeters. And you have an IC here, all right, an integrated circuit chip here, all right, which you can open out, and we keep doing that, all right. And when you do that, you see a circuit once again inside this, except that now all the tracks are on the scale of micrometers, okay. And inside the IC, as we've just said, there are further ICs, there are transistors, there are all sorts of other things. And so you can now open those out. And the moment you do that, you see something of this sort, which is on the scale of 100 nanometers, all right. And you have this strain of gold out here, and the whole thing is on silicon, all right. You go one step further, and you start seeing this, by the way, is with a microscope that we ourselves have built. These steps that you see are roughly on the scale of atoms, all right. They're just a few atomic, atoms deep. And go one step further, and you start seeing atoms right now. And these guys have reached the point where they're now working in the 5 nanometer range. And you have in nature and so on, you have people actually working and making circuits at the atomic level. Forget about elsewhere. We ourselves are beginning to do that in our own lab, all right? I mean, this is after I left ITK and started off this whole thing, because we just, at the rate at which things were happening, they happen inside academics. You're never going to get anywhere close to being able to do anything on this type of a scale at all. All right. So you have to somehow get out of that and start working with a completely different mindset. Okay. And that's what I'll now take you through. All right. So now the key technology is that we had to, so suppose we want to build a mini fab. All right. That is what you start with. Okay. And when I say we, I don't mean the government builds the mini fab. We means we, you, I, Vijay Raghavan and so on, right? And Prabhu maybe, Ravi. We get all these people together and we say, all right, let's just build a mini fab. What do we need? What will we have to do in order to make that happen? All right. So now the first thing, the technology that you have to somehow master is the ability to start making pure silicon, ingots of pure silicon, and then you start cutting those into thin wafers. All right. Of course, the next thing is controlled deposition of thin films. Why do they have to be thin? Well, obviously, you're miniaturizing everything. Right? If you're going to try to put 114 billion transistors on a single IC, everything has to be very, very small. And you start by all the layers and everything that you use, the metallization layers and everything else has to be really thin, as thin as you can make it. And the thinnest that you can go to at the moment, all right, is 1 atom thick. All right, that's why the name of or the title of the talk was Atomic Layer Deposition, because there you have controlled deposition, 1 atomic layer at a time. And that's the machine that we've just built. And I was myself, and this was my introduction to it. We built the machine first and then started using it. And the very first deposition we did completely zapped the hell out of all of us. I'll just show it to you. Because that was the first time I said, wow, yeah, this thing works. All right, this whole idea and the whole technology is quite remarkable. Yeah. All right. The type of finish that you get on the deposition, all right, is something that we'll just show you the thing. All right, and now the why thin? Because of miniaturization. Obviously, cost cutting. Each one of these materials costs a certain amount. The less you use, and you use exactly the amount that you want to use, or not more than that. That will keep the costs at whatever they're going to turn out to be. Then you have control of homogeneity, uniformity. If you've got bulk material and you're trying to dope it, getting all these dopants right in and making it completely uniform across a thick piece is going to be much more difficult than across a thin piece, right? So all of that. Then comes doping, masking, in order to make each one of these transistors completely independent, all right? And then you have etching. You will, there are parts that you sort of, the masking is because only you deposit in certain parts, and then the rest of it you have to etch out. So you need etching, you need lithography. And then eventually, once you made the device, you want to be able to test it to, current versus voltage characteristics and so on, okay? Now, okay, so now let's, so how do we do this in India, all right? I'm not interested in doing it elsewhere. We do it where we are, all right? In fact, forget about India. We're talking about doing it in Delhi, and in Delhi, it's South Delhi, all right? It's where we happen to be. So that's the problem that we have to solve, all right? Now, so we need to build an ecosystem. It's not, you can't just build a lab out of thin air, yeah? You can't do it in a vacuum. There is a certain technological base that you need, all right? So you have to know where you can get things machined, who knows what. Once you hand it out to somebody and you say, please, do this for me. You have to know whether the guy will actually do it or he returns something that you'll be pulling your hair out with, all right? So now we need to be able to build the instruments with which we're able to build all of this. We need to also then be able to set up experiments using those particular instruments, okay? And then you, of course, are going to require a fair amount of theory. The key skill that we picked up as from the background in theory is the ability to conceptualize and put, and define a certain structure to a whole set of facts, which is what in part we're trying to now do. We're trying to demystify this whole process that took place from 1947 to 2024 in this whole industry. What were the, I won't explain all of them because I have to relate it to what we are doing, but at least pose the questions. And the reason why, so this whole concept that you do theory to the exclusion of experiment and so on, all that has to go out of the window. The whole thing has to be seamless. You are setting up the experiments, and it's not the type of theory which is purely mathematical and is completely cut off. You are given, you set up the experiment, you get a certain set of results, and if they're not coming out the way you want them to come out, you have to theorize about why, where things are going wrong, and your theories will be tested by your claiming that now if you do this, the results will all straighten out. All right. Now that kind of theory is a completely different kind of theory from the purely mathematical type. All right. It's a, but, and then a lot of it, to understand that, to understand that, you will need computation. And I'll explain this in a slightly different way, because all of us who were coming out of theory, pure theory, had a very low opinion of computation. That opinion has been revised now. All right. And for those of you who have the same problem as we had as theoretical physics, I remember Ken Wilson once giving this talk in which he said that I want, and he was speaking to a whole bunch of us who were all particle theorists, all right? And he says, what I want all physicists to do is that whenever they look at a problem, they immediately calculate how much computer time is going to be required to solve this. And I remember walking out of the room, and this is one of these people who was next to me. He says, Deshdeep, if this is what physics is coming to, I'm getting the hell out of physics. So that was the attitude. But all right, but let me explain to you. I mean, and that was the feeling that I also had. I also was planning to get the hell out of physics if this is what it was going to come to. But over time, that whole position has been completely revised. All right. And so what I'll do is I'll explain it this way. I mean, in the 1880s, all right, we'd already started looking at spectra. And whatever, it was in fact easier to get the mercury spectrum out than to get the hydrogen spectrum out, because a huge number of the lines in mercury are in the visible, all right? But now suppose you have to calculate the spectra, all right? Hydrogen you can get, it's part of every single quantum mechanics course. Helium, you're already, turning and twisting and using variational methods and trying to get just the ground state out and all that. Lithium, you put up your hands, all right? Boron, beryllium, boron, carbon, you say, well, forget it. All right. And of course, Hartree had already, in the heydays of quantum mechanics, in 1928, he'd put down the equation for solving the thing in general for any atom. And by the way, of course, if you come to molecules, it becomes even worse. All right. And then, of course, Fock realized that these were all our electrons were fermions, so you had to anti-symmetrize the wave function. So then the Hartree-Fock equation was in place in about 1933. And that's it. It just remained where it was until the 60s when computers came in. And that's the first time, that's the first problem all physicists pounced on, because they'd been waiting to figure out that breakthrough had to come. And then they started calculating the spectra. So of all the infinite number of spectra that you could calculate and you would need to calculate, the only one that you can do with pure analytic theoretical calculations is hydrogen. All right. That is a sobering thought. Yeah? The rest of it requires computation. So you need computation and you need that base and you need the set of skills and the understanding of the computer and how you can make it. Very soon you start running out of computer time and the speed and all that stuff. You really have to be interacting with that whole thing. And those skills have to build up. Without that, you're not going to get very far. And theory, of course. All right. And so the plan then, all right, was that we would start building instruments indigenously, all right, from the ground upwards, okay? And then enough of them to get a whole lab and eventually then start doing research, all right? So now the rest of the talk is how far we've managed to go with this, all right? So now let's, since one of the things with which we started probing all these semiconducting devices was, yeah.
It's like indigenously integrated laboratories means
Every instrument has been built by you.
built by you, not procured from an Indian source.
Well, we have, for practical reasons, yes, we have. We've allowed ourselves to extend the meaning of indigenous to getting it from Indian sources. If there's any other Indian company that has built it from scratch, we just get it from them. All right. So the competition is entirely with imported instruments. Okay. So and so one of the things that we built with which we were able to now look at these ICs and etc. was this tuning fork AFM. So you get all these crystals which you can open out. They're generally inside an evacuated thing, and you have a tuning forks and you get them oscillating. You can excite them, and they have very precise frequencies of, in this particular case, 32,764 hertz. All right. You open it out, the moment it comes in air, there is friction and all that stuff, the resonance frequency comes down a bit. All right. But now if you bring this tuning fork, and you then have to figure out a way of putting a probe on it. Sorry, this one. You put this probe. So we had to build a jig with which we could stick this right on top of it very precisely, all right? And then etch it in order to get that sharp tip. Now you bring this close to a surface, all right? This is oscillating, but as it comes close to the surface, it starts feeling the van der Waals forces on the surface, all right? And those are attractive. So it sort of tends to stick to the surface slightly. And it takes just that much longer to come up, which means that the time period of oscillation increases slightly, okay? And which means that the number of oscillations inside a given second now decreases because the time period has gone up. Now you can measure the shift in frequency, all right, using a lock-in amplifier, which also we had built for other reasons, okay? And you had to modify it slightly, but so, I mean, the people who had built it in right now in this company come research group claimed that they could actually pick out a shift in frequency of about 3 millihertz in 30,000 hertz. Okay. So you're talking about 1 part in 10 to the 7. And I said, well, I'll believe it if and you use the shift in frequency, all right, because of the van der Waals forces, the delta F to image the surface. All right. So this is an 18549, all right, analog devices. You open this out, and this one is the top layer. We've downloaded this thing from the website, okay. And you can see out here at this point, 1985 ADI written out here, all right, which is Analog Devices Incorporated. We now we use the AFM, and this was one of the first images where we saw the AD and the 1985. This is while you're scanning in this direction, and this is in the retrace. You picked it out. So you said, and this is coming from the delta F. You're taking that information. The entire information of what there is on the surface is in that hesitation. of the tip as it goes down and it comes up. Just that hesitation has the info. Yeah. It's remarkable. And so we said, wow, yeah, this is really working. All right. I mean, everything had to work, your electronics. And the electronics was built, from scratch. I mean, we built, there was no bought out component in that whole thing. Okay. So now this one, and then of course you scan more and more of it, and you then stitched it together through software. Okay, but it was something with which we can actually probe these ICs. I mean, the 8549 is actually quite expensive, but we blew quite a lot of them. And so we said, all right, at least we put them to some good use here. So we could at least use them as samples for testing out our tuning fork AFL. All right. Okay, now let's get back to the main focus of the talk, which is the deposition. Okay. We'll come back to being able to probe things once we've gotten to the stage where we can build a device. Okay, and then we have to also be able to characterize it. Now, the various thin film deposition techniques, all right, are that you have all these chemical ones, where we built a spin coater. Spin coater is fairly useful. And the rest of them we've gone down this particular alley. So chemical vapor deposition, we've not built an MOCVD as yet, all right, although hopefully now that some expertise is there on that in the country, including here with Arnab and his group, it's something we can look into. But the low pressure CVD, the thermal CVDs, and the ALDs, these are things that we have actually built. And not just built, we have now installed something like 20 thermal CVDs. And they've started producing a fair number of papers and so on. And we ourselves, we'll just show you some of the results that we managed to achieve. And again, this has been built from scratch, right? Every bit of when I say that we built it, it means that we've designed and machined every mechanical component with our own hands. We've designed and soldered all the electronics. We've written every line of the software. And in many of these cases, many of the materials also we've synthesized ourselves. All right. So it's really, it does require a bit of patience to go through that, but we have done that. And then the other route, this one, thermal evaporation and sputtering, that is available to, it's at least there are other companies in the country that have done it. Although a huge amount of the electronics, etc., is still imported, right? I mean, then they haven't. In our thing, there's, let me put it this way. These thermal CVDs were being imported from abroad for, I mean, SSPL bought one for 1.10 crore or something. We have built a better CVD, all right, and I will hopefully convince you that it is better, and brought it into the market at about 25 lakhs plus GST, all right. And the import component in that, the amount that we've had to get from outside, is probably about a lakh or something. It's about 2-3%, maybe 4%. All right. So we are interested in selling those CVDs abroad, because if it's only 4% and you sell one, you can buy components for another 25 CVDs. All right. And you keep the whole thing completely dollar neutral. I mean, the number of dollars that you get and that you send out remains equal. All right. So now let's look at a comparison between the atomic layer deposition and the chemical vapor deposition, because it is only in the course of building these and beginning to use them that we also discovered all the favorable properties of each one of these. All right. Now, the growth rate in this case is 0.1 nanometer. 0.1 nanometers is basically an angstrom. So you're going from one atomic layer at a time up to about 10 layers in a minute. All right. So you do it repeatedly, but you can do it one atomic layer at a time. And the second thing is with the CVD, you can do about 10 nanometers to 100 nanometers. And PVD, which is physical vapor deposition, which is sputtering and thermal evaporation and so on, you can go from about 100 to 1 micrometer a second. All right. Obviously, if you want a thick coating, then trying to do it 1 atomic layer at a time is a bad idea. Okay. It'll take you ages to build it up. And then the next thing is conformality. All right. And this is very, very conformal. Now, let me explain to you what conformal means. All right. Because if it's physical vapor deposition, it is just going to be very directional. So if the vapor is coming from this side, it'll just deposit right on top. In atomic layer deposition, it will just completely cover the surface and it'll be just uniformly thick everywhere on the surface. Now, the example that made the importance of this clear to me was, let's say, a supercapacitor that you're trying to build. Okay. So what you have to do is that let's think of just what's it, the normal one plate, a dielectric, and then another flat plate. Okay. So the capacitance of that is epsilon A divided by D. All right. A is the area of the plates and D is the thickness of the dielectric in between. All right. So if you want this capacitance to go up massively, you want to increase the area, A, you have to increase, and you want to decrease the thickness of the dielectric in between. So how do you increase the area? Well, you start making indentations inside the thing. So instead of having just a flat plate, you'll start making sort of holes inside it. And inside the holes, you make further holes and so on, right? So you keep indenting the whole thing, right? And then the next thing that you want to do is that you want to cover this with the dielectric layer, which ideally you try to make it 1 atom thick. The only problem is that if there's a small pinhole there, and this is a supercapacitor, so you're going to have a huge voltage. Through that pinhole, you'll have a breakdown, all right? And the whole thing is just going to... so you can't really make it just 1 atom thick. It'll have to be like 10 atoms thick at least, all right? So that all pinholes are taken care of. But it has to be conformal, because if all the holes that all the indentations that you made get filled up, all right, then you're back to having just a flat surface again, right? So it has to follow exactly the shape that you have. So that's where the conformality comes in. And then you have a metallic layer on top, which also follows that shape. So now you get the advantage of that extra area, but only through conformality. And that you can get through atomic layer deposition. Okay, and then, of course, here in chemical vapor deposition, you're going to end up with something that looks like this. And it is, a continuous process. Okay, so now the first thing that we did was and how does this work? All right, how do you manage to get exactly this conformality, and how do you get it to be exactly 1 atomic layer thick? All right, now that is, so let's just actually look at the deposition of Al2O3. All right, now in this, the key, all right, is that you let in, so you have what you're depositing, you're finally going to make aluminum Al2O3, all right? So you need a source of aluminum, and then you obviously need a source of oxygen. Otherwise, you're not going to get Al2O3, right? I mean, but in this, the key is that you bring in, so you bring 2 reactants in, okay? But you don't bring them in at the same time. You bring them in 1 at a time. So and what are the reactants? You have, the 2 reactants A and B, all right, are trimethyl aluminum, which is TMA. And what is trimethyl aluminum? Is just an aluminum. Let's just go to the next one. So it looks like this. You have the blue thing is the aluminum atom. And to that, you have three methyl groups there. I mean, CH3s added, stuck to that. And then water is the other thing. But I mean, this is distilled water, and I mean, I shouldn't have other contaminants and so on. But that is now so first, what happens is that you bring in the water, okay, and the H2O. So the green things are the O's, and the white thing there are the H's. All right, and H2O comes in, and it just sits on the surface. The surface is slightly reactive. It gets rid of one of the hydrogens, and then two hydrogens come together. They form H2, which is gaseous, and that just hangs around until you sweep out. Then you have you bring in a flushing gas. You use argon or something, and you flush it out. But this thing now covers the entire surface. All right, and so you've got these dangling hydrogen bonds. And this is what the thing looks like. And the whole surface gets covered. And after that, the H2O doesn't react with itself. So the rest of it just hangs around until you've flushed it out. And once you've flushed it out, then everything is very clean and you have this single layer right now. Okay. Now you bring in the next pulse, you bring in the TMA. And the TMA is this trimethyl aluminum. So you have these types of. And now the aluminum, which is the blue thing, reacts with the oxygen, all right? And it comes and sits on top of that. This extra hydrogen just combines with one of the CH3s. You get CH4, and that CH4 then just hangs around once again. When you flush, it'll go out. And so you end up with something that looks like this. Now you bring in the H2O again, and the extra hydrogens will combine and will turn some of these CH3s into CH4s. And that once again comes out, and you clear the whole thing. One more step, and you're left with something that looks exactly like where you started off with. You have this one layer that has gotten deposited, and you have the sort of the hydrogen bonds sticking out once again. And once again, you can go through the cycle. So if you just send in one pulse, so what is the pulse? It is H2O followed by TMA. I mean, H2O, then you flush, so argon, then TMA, argon again, and you're back here. And you've got one atomic layer. And it will just follow because this is reacting on the surface, right? So it will just, wherever atoms are available, that's where the deposition will take place. And it is self-limiting, all right? So this is what happens here. And this is the system that we built. Well, right now we don't have the in situ measurement, but that's something that we would need to now start putting in. Right. That's where. So we have a collaborator in ISRO who worked in precisely this area. I mean, he has a dual PhD, one in electrical engineering and one in physics, and he's the one who. And that's why it worked out. So he came in and he knew exactly where, how to optimize this whole thing. And we'll just see in a moment. So we've got this reactor out here. This is the whole gas delivery system, and all the electronics, etc., is below. So it took some time to design the entire heater for this. This reaction takes place. I mean, you have to keep the surface and at a particular temperature, and has to be very uniformly heated. So the heater had to be bound with 3 separate parts, because on the outside you lose more heat. So you have to differentially feed in heat and so on. All right. So all this, of course, these engineering aspects were there. I mean, the temperature control, and you had to keep the walls also, and you had to heat this entire thing. All the mass flow controllers we built ourselves, all right, with 1 part in 10 to the 5. And so this is the whole GUI. All right, and it was all computer controlled. And these are the pulses that we gave, and this is the final result. This is 250 pulses, this is 500, and this is 750. You see the color change as it becomes thicker and thicker. And you can see that the quality of the finish is just a mirror finish. So it was just by looking at it, you know that you are getting the depositions that you want. And this is the conformality. There was just the reverse side. It wasn't completely sitting on top of the heater. So there was the possibility of the thing coming on the reverse side. And so you got this because it's conformal, right? So even the other side gets coated by that amount. And this is on a 4-inch paper. All right, we got this. All right, so this one, so the rest of these depositions are now going to be done by our collaborator in ISRO. We're using our thing and it'll be optimized. And so we then reasonably sure that we can at least do these depositions for gate oxides and capping layers for nanostructures and multi-layer memory devices and so on. All right.
How many of these?
Well, we haven't gotten to that point. We've just managed to complete this, got the first few depositions done. We've now shipped the first ALD. We're building a second one for ourselves. All right. And the first one goes to ISRO. The person has already done this earlier, so he's very confident. And because the very first one also worked out that well, we are quite confident that he'll be able to do it. And then once that happens, then at least we know that much of technology is under control. We then go to the next step. Okay, you can do heterostructure. So instead of just doing A, B, A, B, you can do A, B, A, C, A, B, and so on. All right. And then so we now, you have Bennick and Oxford Instruments. These are the two of the leading MNCs. And we, at least for the base model, we have all the specs that they have. All right, we can take them on 100%. All right. So this one, all right, and then the chemical vapor deposition system is this one that we built, and we can have precursors which are either solids, gases, or liquids. And this is the one of which we've installed 20 of these. All right, and there's a whole bunch. So hopefully by the end of this financial year, we'd have gone up to 25 or 27 of these. Okay. This one, I'll just give you an example of the types of depositions you can do. You can make graphene, for instance, and the whole basic recipe is that you just take methane and hydrogen and pass it over a copper foil at 1,000 degrees. You do, how that happens is we'll just speed it up. I mean, we won't get into the details of how it happens, but we'll just show you some of the results of. Now, the way you actually detect that there is graphene on top is that you've heated this whole thing up to 1,000 degrees, and let's say there is a thin layer of graphene, which is just 1 atomic level deep, right? Which is formed on top of it. It's very difficult to see it. What happens is that when you cool it down, the copper shrinks, but the graphene doesn't shrink as much, and therefore there are wrinkles that develop in the graphene sheet. It's the wrinkles that allow you, because there's a certain amount of reflection from the wrinkles. I mean, if you're looking out at water inside a pool and it was completely still, you would probably not be able to make out that there's water inside. All right. If there are slight waves, then that's how you pick it out. That's exactly the same thing that happens here. So we do this. This is just the copper foil before annealing. There are lines because the foil has actually been extruded between rollers. All right. You anneal this thing. All right. And you get these, the lines become less prominent, but you get all these grain boundaries. Now you deposit graphene on top. It's very difficult to make out that there is any graphene here. You go a little further, you zoom a little more. Now you can start seeing these. There are wrinkles that you see out here. There are some lines. To go one step further, here now you're beginning to see these lines out here. So that's how you know that there is graphene there, all right? Now, the next thing but in the meantime, we had built an STM with which a scanning tunneling microscope, right? With which we could actually pick out, with which we can actually go all the way down to atoms. And so instead of just looking at these wrinkles, all right, using an optical microscope, we turned on the scanning tunneling microscope, all right. These were the very first images that we'd gotten. I'll skip those, but and this is the form in which we have now built 60 of these, all right, and have installed them, including one in Singapore and so on. And that was a wake-up call because there was a student who had done his PhD and who'd used this, the STM, and he went to Singapore and they were thinking of buying an STM. So he said, oh, but my country he became a super patriot. He said, my country is also making them and this and that. So they wrote to us, asked us for the specs, and then they put up the specs in a global tender on the government of Singapore website, which we easily won, all right. And we went and installed and that was it, all right. We got...
What fraction?
Well, there we had pushed up the cost a bit to make it look more respectable. This one, the air STMs, we're doing for about 12 lakhs. All right. And the vacuum STM, with which low vacuum, 10 to the minus 3 type of stuff, but it holds the vacuum for like 4 hours. Okay. That, right. 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 Okay. Yeah. All right. We'll discuss that over coffee. We go to about 10 to the minus 3 at the moment, but we are trying to push it up. So the first thing we made is a gauge, because we have to be able to measure it. So in collaboration with BRC, we made this gauge which goes up to 10 to the minus 9. So it's the full range vacuum gauge. We've been able to test it only 10 to the minus 9 because we've not been able to access chambers which go to 10 to the minus 10 and 11. All right. That itself is a problem. Anyway, so we built this. And now with this, we looked at the wrinkles, and now you see these wrinkles. And this is a beautiful image where you see the wrinkles and you see these benzene type of rings. You see the atoms very, very clearly on the wrinkles. All right. And so this one, these are some of the prettiest images. And this is when you've got these sheets at an angle with each other, and you end up seeing moire patterns. And you see this is on a larger scale. So these look like atoms, but they're actually moire patterns. All right. And so we finally wrote this up and published this. So the CVD was fully made by us, and the STM is also fully made by us. And we were able to put the whole thing together and produce a paper which has just been published. And so the significance is that we've used no bought out and no imported equipment at all in order to produce this paper. All right. And this has given us the confidence that we can now write, at least 6, 7 more papers with absolutely no bought out component. No bought out instrument at all. All right. It's completely, whatever has happened in those rooms. And the space we have is about the size of this room. All right. But we have gotten the thing working. Now, with that, then we also produced MOS2. And there are different types of structures. One of the things that you do is, can you produce these molybdenum disulfide of a sufficiently large size that you can make contacts on it, and this can be really thin, like, again, just 1 atomic layer thin or thick. And so this is, we were able to do this, go up to, well, in this particular case, as much as 90 microns, 73 microns, and so on. All right. But you can also make these dendritic structures, all right, which is like a fractal structure. You have these things that come out, and then out of each one of these branches, you get branches, and then out of those branches, you get further branches, and it keeps going like that. And if these branches have reactive sites, all right, then the number of reactive sites now multiplies, and you can, if every reactive site can be used to catalyze a particular hydrogen evolution reaction, for instance, then, and you can build this also in 3 dimensions in a controlled way, then you would get a much better catalyst. And so this is another paper that we wrote, and which has been accepted too. In this time in, these are journals that we're getting to know only after we write the papers. But this happened to be nanostructures and nano objects. Does that sound like a journal? We are the academic group, yeah. I mean, what do you mean? Which no, we're running a PhD program also. The PhDs are being granted by NIT Calicut, but all the research and all the papers are being done inside the company. If you have only this much space, all of it is an R&D lab, because I mean, you can't. I mean, there's also production going on, and there's also R&D going on in the same place. Right? No, so it is. We need the R&D, because without the R&D, we don't know which direction to move in. It's the R&D that gives the direction to the entire the technological aspects. So this whole thing, that's what I meant, that when we make this completely seamless, I mean, this is between engineering and when you're setting up the experiments, there's you have to keep modifying the instruments themselves and make them more and more powerful. So all of that has, I mean, the loop has to close locally. And that's what is happening in this case, as you're seeing. But and one of these papers that I didn't think, this is not the one on dendrites, but it is another one which I didn't think very highly of, but it seems to have made it to the cover of at least this journal, which is a Journal of Vacuum Science and Technology. All right. And then now the thing is that if you've got the STM and you can control it, if you increase the bias, right now the bias that we're giving is going up to about 100 volts. But we can increase the bias to 1,000 volts, in which case the electrons that come out, and you'll have to take it out of the tunneling range. I mean, it's more the field emission range, all right? The electrons will come and hit the surface with 1 keV of energy, because right, it's just an EV times 1,000, all right? And that is enough to start knocking atoms out, okay? And so now you can actually do lithography on the atomic scale with this, all right? And once again, if you start getting that working, you can certainly write papers without a problem, all right? Now and then we've also done stuff which allows us to characterize the devices. So one of these things is we have still another 5-7 minutes, right? We started at about, right? So I'll finish in that much time, okay? Hopefully, yeah. All right. So one of the things that we did with, again, these instruments, so we're not buying Keithley or anything of that sort, right? We can measure resistances over 20 orders of magnitude, from 10 to the minus 5 ohms all the way out to 10 to the, under the best of circumstances, 10 to the 15 ohms, but without any hassles up to 10 to the 14 ohms, okay?
It's also part of.
Yeah, well, not independent yet. We've sort of made them part of this thing, but we are thinking of making them independent, so people can then buy these just as standalone things. Now, So we can verify this formula, this diode formula. And just very briefly, you have this exponential, and this is the voltage across the diode, and you have -1. Now, if you reverse bias this, so this is e to the minus something, this exponential becomes negligible, and you just get the diode current just becomes minus IS, all right, the saturation current. On the other hand, if this is forward biased, then this 1 becomes negligible, and the exponential is the only thing that survives. And now you have the current increases exponentially with the forward bias voltage, all right? And we then sort of measured this, and we've just to fit it onto the same page, it comes like this, and then it goes like that. So this is the saturation region out here, and so the red part is the experiment, and the blue one is the formula itself, all right? And we are now measuring the current all the way down to 0.001 nanometer. So we're going down to 1 pico, nanoampere, and we're going down to 1 picoampere. All right. And this is again with electronics that we built from scratch ourselves. All right. So we've not. Okay. So now this is, and then this is with the Xena, which has breakdown voltages, but this was done automatically as a function of temperature from 80 to 440, and we just programmed it. So it would just increase the temperature by 20 degrees at a time and take the full curve. And when it's taking the full curve here, you've got the, this portion is just almost, sorry, this portion is almost completely conducting, and here it's almost completely insulating. So when you're making these measurements, you have to keep switching between current sources and voltage sources, and all that has to be done automatically. So we just left it alone. It used up about 3 liters of liquid nitrogen, and it took about 7-8 hours to make the measurement, but we got the curves out at the end of it all without any other intervention. All right. And then we can also do this spintronics is again, after building these and then starting to use them for doing stuff, I just discovered this stuff is again totally fascinating. I mean, you have electrons, and you built all of electronics based on the charge property of the electron. It has a charge, but it also has a spin, and you can use the spin to manipulate electrons and do all sorts of things. I won't get into this in detail, but we got some of these devices, and you can see the hysteresis loops and so on using the equipment that we built, right? And then so now if we go back, we have then not done too badly here. I mean, this thin film technology seems to be accessible. Lithography seems to be accessible. Testing of devices also seems to be accessible with what we have. We are now looking into doping. We haven't done the doping, but I told you that we've installed 20 of these CVDs, of which about 5 or 6 have gone into electrical engineering departments. And those people have been using it to build devices. And they've been doing doping and all that stuff with it. So we have to actually, once again, collaborate with them, learn how to dope the stuff, all right? And then at least the doping will, we made an etcher just to clean out the substrate, but we'll have to do better than that if we want to. And the masking, of course, maybe Ravi, we can talk about it, because we start with photolithography and then we have to go further. So it's not, and this thing is going to require a different type of, it is liquid phase epitaxy. But given the technological base, it is possible to make a liquid phase epitaxial machine with which we can actually start making ingots of silicon. So in principle, but this is all in principle, right? We could take the whole thing through, all right? It's not completely out of reach. I mean, the situation is not completely hopeless. So we have to first consolidate the whole base. So we've the total number, we built 56 air STMs, 4 vacuum STMs, and 3 low temperature STMs. We've taken it down to about 100 Kelvin. We built 37 of these physical quantity measurement systems and installed them at various places. 20 of these fully automated chemical vapor deposition systems. This one ALD, now we're building the second one. And we built various high-speed data acquisition systems, all of which have gone into one corridor in IIT Delhi. We started by building one for one of the faculty members. Then the person next door came to us and said, hey, why don't you build one for us also? And then it was like dominoes, office by office, people started approaching us. All right. And then, and so we now have this joint PhD program with NIT Calicut and BITS Pilani, MOUs with ISRO and the Inter-University Accelerator Center, which has been very supportive. In fact, the STM was Anjan, Kumar Gupta, and Kundan and Ajit. They all, I mean, it was a combined effort of all of us to get that working. Now, through technology transfer, and it's turned into a collaboration because now there is information flowing back from us to BARC, and so it's a two-way street. So we built this full-range vacuum gauge, and also this triode and the diode sputter ion pumps, which allow us to then get to much lower vacuum, and that will allow us to start doing things in UHV. Okay, I guess we've suddenly come to the end of this. All right, in just the 1 hour that we were supposed to. Okay, yeah. So I didn't know how to capture all of this in a title. Yeah. So I guess that title was probably misleading. Yeah. Oh, it's only 24, yeah.
And what's the background so that the students might know who these people are?
No, well, IITK has contributed about 100 man-years of work to this place. But I left IITK about 10 years ago. So after that, it's sort of, but I didn't manage to get.
Employ these people after sharing
before that, yeah, long before that. I mean,
they get spoiled on
they have to be.
Yeah.
No, you have to start working on them from first year onwards. Yeah.
Okay.
First year of their MSc. Interestingly, it's mostly the people who've come have all been 5-year students.
Okay.
Except for one 2-year student who's actually built many of. I mean, he was the person who could build a lot of this electronics. And but the mode of teaching and of training has to be completely different. I mean, 5 minutes after the person comes through the door, you make him or her sit down with somebody who's building something, and you say, just watch what this person's doing, and he'll keep explaining it to you.
Mm-hmm.
And then you get the whole thing built from one end to the other, all right? And you resolve the atoms, let's say, with the air STM. And after the person's watched, and then there are bits and pieces. So it's the apprenticeship mode. Bits and pieces are sort of handed out to that person. And you say, all right, do this much, and we'll test it. And then after you've done 2 or 3, and he's at least seen the process from one end to the other, then you make him or her. All right. By the way, there are a number of hers in this also. All right. There are the CVD. All right. The Chemical Vapor Deposition System. The person who headed the team for some time was a girl who came high school plus 2 years of ITI, and she was 19 when she joined, and then till about the age of 23 or something, she was doing CVDs. Now she's doing ALDs, and after she's made 4 or 5 ALDs.
So
then I guess
that is the level of training that you need.
Huh?
You don't need any formal I mean, you like people of that,
No,
that kind of training?
you see, the skills that are picked up in college are not these skills. That's what I've been also trying to figure out. The skills are predominantly mathematical skills.
Yeah.
All right. So all the time that we spent in college, we were all the time working with math and trying to relate the math to the physics. But we were never building anything that worked. All right.
Yeah.
It was, and so it's a completely different way of training people. Now, the mathematical skills can feed into computational skills. All right.
Not this.
But not into this. At best, it's computational skills. All right. But even within the computational ones, you can actually get people to use computers without necessarily getting too deep into mathematics. So the skill that we have seemed to have emphasized the most is just that mathematical skill, right? And unfortunately, the skill has become an end in itself without relating it to anything outside of that.
I know.
So and the way in, you see, the way in which, to come back to the question that had puzzled me right at the beginning, the way in which the whole semiconductor industry is taken off, it is not simply that these technical and technological breakthroughs took place. It is that the moment these people were able to build these microprocessors, and the microprocessors could go into PCs and so on, suddenly there was the market for PCs grew at an exponential rate.
Yeah.
And therefore, there was now money coming in to building and keeping on. So unless you had that requirement, see, the only way we can build up the skills here, I mean, when I say that we built 60 of these STMs, that has allowed us to build a certain level of skill, right? Because when you make 60 of them and resolve atoms with every single one, eventually you'll have people who can just do that, and they can do that standing on one leg. All right. And that is a very useful skill now, because that gives you a technological base. But if you built only 2 of them,
It doesn't help.
then you don't have the skill. You're not even sure of the skill. All right. So now that we've got 20, so the market, the feedback that you're getting from the market is not just the money, but it is also the money is allowing you to produce more and more of these and to start consolidating the skills. So if it's a purely academic exercise, you'll never get this level of stability to the technologies that you're building, and you won't be able to build on top of that. That's why, even though in principle, all right, we could have just taken grants and applied and through proposals, and we've consciously not done that. I mean, it has to come from the market, it has to come from the users, and the PhD program is necessary because we also need the users in-house. We can't depend on users who are sitting we're in Delhi, and then the users are sitting in Bombay, let's say, or in Kerala or elsewhere. You have to have users in Delhi. They can talk to users in Kerala or Bombay. Whatever those people are saying, we reproduce in the lab in Delhi, understand it, straighten it out, and then go back and provide the feedback. If it is people there who are trying to do this, it becomes much more complicated. So it's a whole process that is now somehow opening up. All right. And as you can see, it'll take a bit of time for people to even want to listen to. I mean, I'm reasonably impressed with the audience. Yeah, I mean, it's at least what you had promised, about 20-25 people. But it could have been better.
To probe the surface,
Right.
which used a pin. It was
Which
attached.
used a
There was a pin that.
the tuning fork AFM.
Yes.
Yeah, right at the beginning. Yeah.
So
Is there a significance of the frequency that you are using? Does it have to be a certain frequency?
No, we've tried with different types of tuning forks, but this one is the least expensive. I mean, the 32,764.
Standard crystal.
It's the standard crystal, so we just bought a whole bunch of them, and we're using them all over the place. So we sort of buy 100 at a time. So anytime you need a crystal, you just take it out of that bunch. But we've also tried it at higher frequencies and all that stuff. But then you have to tune your whole lock-in amplifier. In the lock-in amplifier, you're able to lock to a particular frequency, so the deviations from that can be easily picked out. And so it's
Talk about the people whom you are trying to bring in and train, but what was the core team?
the core team was this.
How many?
The core team to begin with was me, with a background. I'd never walked into a lab willingly until I decided to start this off. And it was, right now, once I became convinced that there was no other way forward, I was working, the first set of courses I taught were all theoretical courses. After and up to, Shiraz's batch passed out in 95 or in 95, 96. After that, I tried my level best not to ever teach another theoretical course, because every time I taught a theoretical course, there would be 5 string theorists who would come. And I said that this has to be stopped. I told Shiraz to come, but I told him that this is going to be a brainwashing talk. So,
Cooperative question.
yeah.
What is
this is
Quasar
not recorded,
Technologies
yeah.
Private
It's
Limited?
just hybrid, right? Not recorded.
No, it is on YouTube.
Yeah. This is
So I'm trying to understand what is this entity, this
Sorry.
Quasar Technologies, because it looks like a company. It also looks like an R&D lab.
Yeah,
It
it's
also
three
looks like an
things- three
educational
things at the
institute.
same time. All right. One is, it is a company in the sense that we have not asked for any grants from anywhere. All right. And we have supported ourselves entirely from the market. We built things, sold them, whatever money we've gotten, we've plowed it back into building more stuff. All right. So to that extent, it's a company. It's self-supporting. It's a self-supporting financial unit. All right.
Okay, that part I got. But then, are
The
you
second-
scale at all? Because I'm
Right,
just
okay.
it sounds like you have a passion to do research, and
Right.
you are funding your research by your own
Right.
side
Through
hobby.
this is one thing, right? But you can scale. So now you can ask the question, how many CVDs can you sell in the country? All right. And my answer is probably 100, 200 of them, but not in a single year. I mean, there 200 in a decade or so. Now,
Yeah.
but right. So now if you've got to go global, then you will have to start setting up the marketing outside. But this is technical marketing. This is not, selling cosmetics or something. I mean, immediately, so we've tried this. We've tried to figure out whether we can get people who, because you have to know a lot about CVDs and ALDs and so on in order to even convince people to buy this stuff, right? And India doesn't have a great image at the moment of being a high-tech hub from which all these, so we go out. So either we can go out and try to sell in Africa or the Middle East, or I mean, the Middle East right now may not be the best place to head to. But I mean, we could certainly do Singapore and Malaysia and Indonesia and all that stuff, or Vietnam. Vietnam is actually doing fairly well.
But Deshdeep, I would think that your customers in India would be your advertisement, right?
Right.
If
So you have to at
if
least
you can get some good work out of here, then people will buy.
then people will buy. And
Yeah.
so the first thing is to get people in India to buy it and start doing good work. So at least our problem was that we started off with STMs, all right, which were fascinating from a physics viewpoint and so on, right? But they were a characterization instruments. So you had to have the sample before you could start using the STM. Now, by switching to CVDs and ALDs and similar things, we suddenly found that the market is wider because people generally, I mean, the way the logic goes is that you buy these, you synthesize stuff, and then we'll look around somewhere to where it can get characterized and so on. So characterization, you go to some central facility and so on. So we're finding that the CVDs are selling, all right? Now, but still, there's no semiconductor industry in India. It's not that everything is within the government sector. If the government decides to invest, then we have some market inside India. So you'd have to then start selling outside, okay? Now, the big problem is that if we sell outside, then first of all, I did have a problem with that, we were trying to see whether you could build these instruments and give Indian research an edge by allowing people to get instruments at a lower cost and with much better support. But now the logic, the whole economic logic is forcing you to start selling these instruments abroad. So effectively, you're producing for an...
Yeah.
Hello.
Right.
Two questions.
Can I ask a question?
Right. Okay.
So
Yeah.
you mentioned that ALD
Can I ask a question?
temperature gradient is important. There shouldn't be any temperature
Oh,
gradient.
there are people there also. Yeah.
Yeah, I'm so sorry. I will ask later on. Let this guy. I'm so sorry. Yeah, I will ask later on.
Yeah.
Yes, sir. The temperature, the uniformity of the temperature gradient in ALD, you mentioned that it is important. What happens if there is a difference in the temperature? What happens to the physics of deposition?
Oh, because then I think the deposition will not be that uniform. There could be areas where it just either doesn't deposit because the interactions just don't take place.
Okay. But because it's self-limiting, can we just not pump it with OH ions until the whole thing is covered?
It's possible, but then that again, all these then you have to figure out the exact conditions and for how long you have to pump and how much you have to pump in order to get it. Whereas if it's completely uniform, it's exactly the same temperature everywhere.
Makes it easier.
Then you don't. As your parameter space becomes more and more complicated, finding the exact point in the parameter space or the exact region becomes that much more complicated, and it makes the instrument that much more difficult to use.
And just one more
Yeah,
thing.
sure. Yeah, go ahead.
How would a
I don't
person
have-
who's done with a PhD or postdoc
Sorry?
start? So for someone who's done with a PhD or postdoc, how would they start looking for a job in your company?
They don't wait till they've finished their PhD or postdoc. They start when they're starting their PhD.
It's too late.
No. Unless you wait, but you start by taking my number and my email address and writing to me. Yeah, I guess that's probably a fair answer.
Yeah.
Good evening, Professor.
You can go ahead. Yeah, please.
Good evening, Professor. Just to the second last conversation you had, maybe having a. I'm so sorry.
Sorry, who is it who's speaking right now?
It's in the speaker. This is Jay Darji. I'm a master's
Yeah,
student
they're
here.
speaking. Okay, fine. Yeah. All right. Yeah.
Yeah.
Go ahead.
First of all, thank you so much for the insightful talk. I'm in UC Berkeley right now.
Right.
And this is very fascinating to listen to Indian scientists like this. Just to adding on the second last conversation you were having, that maybe adding one or two big names, a client with big name or an organization with big name outside of India, and collaborating either with them or either providing them machine with very low rates and good quality services beyond any limitations of services, and having their names on the client list, maybe it will help penetrate more into the global market, because that's what they want. Like if big quality demanding customers are taking your machines, maybe it will help on penetrating on global market as well. I hope I was being relevant on that.
Sorry, the last part was, I mean, what are our thoughts about that? Sorry,
Penetrating into the global market, it
Right.
requires some kind of validation from others that okay, if any, let's say if Google is checking some other third-party company, they say maybe AWS or Microsoft have taken these machines, maybe we can take it as well. So having one or two big client names
Right.
on the
There's no doubt
customer
about
side.
that. If we sell to specific people,
Yep.
and we can put that the but I'm well, that is certainly one thing that would help. But the second question is really one would have to make a trip to whichever country we decide to start selling to, and in some ways I don't and we'll have to explore what the climate is there. I mean the political climate. For instance, one of the easiest countries or seemingly easiest countries would have been the US,
Yep.
partly because so many. I mean, I'd spent a lot of time while I was teaching in IIT Kanpur trying to keep people from going to the US, but this nevertheless went. But as a result, now that now we can take advantage of that fact because there are so many of my students there that I can get in touch with them and see whether they can help with but I'll have to make a whole trip to the US. And to tell you the truth, after coming back from the US, I haven't renewed my passport. So I'll have to start with that.
So in that case, Professor, I will be open to help in any ways possible to you because I'm in California right now.
You
in
yourself are in California.
He is willing to be.
Oh, okay. All right. Yeah.
in Bay Area, I'm actually in University of California,
Why don't you
Berkeley.
take my email address, which is ds@itk.ac.in, and just write to me, and we'll then talk further.
If
Yeah,
fine
you-
with the guy who is managing the meeting and can share your mobile number and email ID, like it will really help because the noise is coming a little bit. And
Certainly. You have Asset's email ID, right, Jay? So you just write to it and we'll make sure that you have a context for professors.
Yeah.
Thank you so much, sir.
If you're
Thank you so
already
much.
there, then we could certainly start. Right.
Yes, sir. And then one more, this was on adding on to what your conversation was, but I have two questions. One was on the tech part and one is on the organization part. Like, how do we manage to think about designing the systems from defining the objective? Let's say if I want to design one machine, what's my objective? What I want to do, and then start asking questions and then figuring out how to answer those questions. Like, if you can give one example of machine you were back in the time trying to build it, and what was your design approach, your thinking approach, your team's approach to build a machine with an example. And then I will forward with myself with an organization management question because it still seems very organizational on the scratch level.
That's
for
sorry
the
to
commercial
interrupt.
Right. What we'll do, this becomes a conversation we should have separately, not as part of this particular talk. So
It will work as well, sir.
the
Yeah,
next
I think it
step
will
is
be too long.
we'll share our contact informations and then we'll just talk about this. If that's
Yeah.
okay.
For sure, sir. For sure, sir.
I'm
It
sorry
is
to
fine. It is
interrupt,
fine.
but we are running out of time. We are already about 20 minutes over time.
Right.
So
I
like,
understand, sir. My
we'll
day
make sure
started,
that
but
you have a
yours are
contact.
going to end.
You can
I
communicate.
understand, sir. For sure, sir. For sure. I'm so sorry. And thank you so much, Professor, once again for this one.
Okay. Fine.
This is a fantastic talk, sir, and I really, really appreciate it. And I'm sure where the people audience also will have. Thank you.
Fascinating.
Yes.